Hi, this is the lecture for Matter and Change for Chapter 2. You need to know what matter is. So matter is anything that has mass and volume. So in other words, matter is anything that occupies space. So that basically means like everything. Everything is practically considered matter. You also need to know what physical properties are. So for an example, if we're talking about people, like a person's physical properties would be like their hair color, eye color, their height, their weight. And now if we're talking about chemical substances, this could be like the density, whether it's a solid, liquid, gas at room temperature, its boiling point, its melting point, okay? It is also important to know that physical properties do not change in their composition, okay? So the composition remains the same, and that is what is really important, okay? The composition of the substance remains the same for a physical property. So an easy example would be if the state of matter is changing from a solid, liquid, a gas. So if we're talking about water, so in the solid state, water is considered ice. But then when it melts, it becomes water, and then when you boil it, it becomes steam. So the composition doesn't change, it still remains H2O. So now we're going to review your three states of matter: solids, liquids, and gases. So on this slide, it only has the information for solids and liquids. The next slide, we'll talk about gases. So solids, the particles are stuck in this rigid structure. They do not move around a whole lot, but they do vibrate some. Then in liquids, we say that their particles slip and slide past each other. So then there is a little bit more movement between the particles. And then if we talk about gases on the next slide. Okay, so now we're going to talk about gases. Now gas particles, I like to describe them as like they're bouncing off the walls. So they're able to move around freely and they're kind of like bouncing around all over the place. All right. Now something I want you to add to your notes. I want to talk about kinetic energy. Okay, kinetic energy. So some of you might know what kinetic energy. Kinetic energy is considered the energy of motion for objects that are moving. So let's talk about the particles in these three different states of matter: solids, liquids, and gases. So which one do you think has the most kinetic energy? Okay, so which one, in other words, has the most movement? The particles in a solid, a liquid, or a gas? So obviously, the one with the most kinetic energy would be your gases. Now, which state of matter do you think would have the least amount of kinetic energy? So the least amount of movement. So yes, that would be your solids, because they don't really move around a whole lot, but those particles do vibrate some. Okay, it's very rigid, a very organized structure, and they just kind of stay put in their lattice structure. All right, next slide. All right, so now we're going to talk about physical changes. So you need to understand physical changes, and then later in the lecture, we're going to talk about chemical changes. So they are the opposite. So physical change basically means that the composition does not change, okay? Although it may take on a different, say, physical shape, but the composition remains the same, okay? So these are some key words down here that will kind of tip you off as that it's just a physical change. Cutting, grinding, bending. So for an example, if I take a piece of paper and I cut it up into tiny little pieces, each piece is still paper. See how the composition remains the same. Grinding. Now some people don't know what grinding means. The best example I can give you is like a coffee grinder. It takes coffee beans and it grinds up the coffee beans kind of like into almost a powder. All right, so see how it's still coffee, but it's just, in tiny, tiny pieces. All right, the composition remains the same. An example about bending, kind of like if I take a paper clip and I kind of unwind the paper clip, or I can bend it into a different shape, composition remains the same. It's still a paper clip. All right, the material is still the same, composition is still the same, but it just takes on a different form. All right, so those are some examples of physical changes, and also kind of like what we talked about earlier about just the changes of state of matter as it's transforming from a solid liquid to gas. Those are also examples of physical changes. All right, so now we're going to talk about mixtures, and there's two different types of mixtures we're going to talk about. We're going to talk about the homogeneous mixtures and the heterogeneous mixtures. So what does the prefix homo mean? Homo means same. What does hetero mean? Hetero means different, okay? So first let's talk about homogeneous mixtures, and I'm going to give you some examples that you should write down in your notes. So since homogeneous means everything is the same, that means that the particles are evenly distributed. Everything is what we say uniform. So some good examples that you should write down for homogeneous mixtures would be water. Water is an excellent example. See, if you look at water in a water bottle, everything is evenly distributed. You have what is called one phase, okay? Which is a phase is like a region that we will talk about later. Another example of homogeneous mixtures like syrup, okay? Syrup is also homogeneous. All those particles are evenly distributed. Also gasoline. Gasoline is also an example of homogeneous mixtures. All right, so now let's talk about heterogeneous mixtures. So once again, hetero means different. So that means that the particles are not evenly distributed. So this might create different regions, or what we call different phases. So in other words, if you see some separation, like between, like if you have a bottle of oil and water, eventually the water and the oil will separate into layers, okay? That is an indicator to you that it is a heterogeneous mixture. Anything that you have to like shake or stir before you use it is probably an indicator that it's a heterogeneous mixture, like ketchup, for example. So usually before you use ketchup, you would probably shake it before you use it, because if you don't shake it, then what comes out? Like water, like watery ketchup. So that is an example of a heterogeneous mixture because the water had separated out. Paint is also an example of a heterogeneous mixture. Usually you have to stir it or shake it before you use it, because the water will separate out of it. Mustard is also an example of heterogeneous mixtures because that is something you would have to shake, once again, because the water separates out, and therefore you need to shake it up in order for that to get dissolved for a little bit till you want to use it. So let's see, let's think about a burrito. I like to use food examples. So let's say you have a burrito, and in your burrito you got beans, you got rice, you got cheese, sour cream, guacamole, whatever type of meat that you like, chicken, carne asada, whatever. So if you have this burrito, do you think a burrito would be a homogeneous mixture or a heterogeneous mixture? So you have to think about it. In your burrito, are all of those particles evenly distributed? Or are the particles not evenly distributed? So one way you can kind of think about it, what if you were to cut up the burrito into pieces and parts? Would each part or piece contain the exact same particles? And the answer to that would be no, because you probably have experienced like eating a burrito, taking a bite, and then each bite is different, right? Sometimes you get a big old bite of like just all sour cream, or you get a big old bite of like just cheese. So that is an example of a heterogeneous mixture. So that is something that you can think of, like breaking it up into tiny pieces. If each piece, if the composition is the same for each piece, then that means that it is homogeneous. But if each piece is different, then that will be an indicator that it is a heterogeneous mixture. So now we're going to talk about phases. So the phases are basically the layers that it may separate into, or the different regions, okay? So they give you an example here. Oil and vinegar, like salad dressing, it has two phases. It'll have the oil phase, and then it will have the vinegar phase. So now let's go to this question over here. Think about this. How many phases do homogeneous mixtures have? Okay, how many phases do homogeneous mixtures have? So let's think about water, think about syrup, think about your gasoline. How many different layers do you see? The correct answer is 1. Okay, homogeneous mixtures have only one phase. Now, how many phases do heterogeneous mixtures have? Okay, so heterogeneous mixtures, which means that they are different, they will have 2 or more phases. Okay, so make sure you know the difference between heterogeneous and homogeneous and the number of phases that they have. All right, now we're going to talk about the different methods that we could use to separate mixtures. So here are some examples listed, the techniques. So filtering is a very good example of a technique we would use to separate a mixture. So I'm assuming that many people know what filtering is. You probably have filtered something sometime in your life. The most common thing you're probably thinking of is like filtered water. So if you're trying to filter water so that you can have better tasting water and get rid of the harmful particles, so you would use a filter and it separates the bad particles versus the good particles. Therefore, you can drink water without the harmful stuff in it. Chromatography and distillation, let's go ahead and talk about those, and I have some examples on the next slides. This is an example of chromatography. So chromatography is a technique used to separate a mixture. So let me go over these diagrams with you one by one. So let's take a look at this first picture here. So you can see in this picture, you have like a bowl of water. So this is like a little dish that has water in it. This is a strip of chromatography paper. And this black line is actually black ink. Okay, it's black ink. So the water here in this bowl, the water is creeping up the paper. As it's creeping up the paper, it's going to come in contact with the black ink. And as time goes by, you can see what happens as the water is creeping up higher and higher to the top of the paper. So it's basically demonstrating that the black ink is made up of all these different colors. The black ink is actually made up of, the little bit of yellow, a little bit of red that looks a little, purple or bluish color. Okay, it's actually a mixture of colors that make up that black ink. Now you're probably familiar with that, like if you look at your ink cartridges from printers. So usually in an ink cartridge, you have just like 3 colors, like the blue, the pink, and the yellow, and it mixes those to get the colors that you're trying to get. So that's an example of chromatography and what chromatography could be used for. So just showing you how it can separate mixtures. All right, now let's talk about distillation. So here is distillation, and this is what the apparatus looks like, the setup. So in this flask here is salt water. So what we're going to do is we're actually going to separate the salt and the water. So this is one way we can purify water. So like if we take some ocean water, we stick it in the flask, this is a Bunsen burner, you heat up the water, it's going to boil. As the water's boiling, it's going to condense, this is a condenser, it's going to condense into this tube here, and then the water will get collected into this flask, leaving behind the salt. So that is an example of distillation and how it separates mixtures. Okay, you need to know the difference between elements and compounds, all right? So basically, elements are pure. Like the elements on the periodic table only contain atoms of that particular substance. So if we're talking about lithium, lithium contains all lithium atoms, okay? So elements are pure in its purest form. You cannot separate them any further. Compounds basically have, as listed here, 2 or more substances in a compound. So a good example would be H2O, water. That is a compound. It has hydrogen and it has oxygen. okay? So in other words, if you take two elements from the periodic table and you combine them, that makes a compound. And your compounds, as stated here, they can actually be separated by a chemical change. And that's what we're going to get into next, chemical changes. All right, so chemical reactions, you have, I know this arrow looks a little distorted here, it's kind of misplaced, but on your notes, it's printed correctly. Sometimes when I download slides and stuff into this program, some of the things come out looking a little off or a little funky. All right, so here's your generic form of a chemical reaction. You have reactants on the left side of the arrow, products on the right. Okay, so that's your generic form of a chemical reaction. So you should remember that. Reactants are always on the left, products are always on the right-hand side of the arrow. So you do need to know the difference between a chemical change and a physical change. So we talked about physical changes earlier. Now we're going to focus on the chemical changes. Okay, the chemical changes. So basically, if a new product is formed, okay, so you see a new product being formed, then that is an indicator to you that it's a chemical change or a chemical reaction has taken place. So you have reactants. The reactants are going to, those atoms are going to rearrange themselves, and then they're going to make something new, which we call the products, all right? So you see something new being formed, that's how you know it's a chemical change. So let me give you some examples of a chemical change, like rusting, okay? If something forms rust, that is an excellent example that a chemical change has occurred, okay? It's iron reacting with the oxygen in the air, and that's how you get rust. Another example, tarnish. Tarnish is kind of like the rust that appears on silver. So if you are familiar with silver, you'll notice that it kind of starts to look dull and kind of dirty. That's tarnish. So that is also an example that a chemical reaction has occurred. Now let's think about an apple. What happens to an apple once you slice your apple, you let it sit on the counter for a little bit? What happens to your apple? So many times you probably notice, well, your apple kind of turned brown. You see the new product being formed. Okay, so that is an indicator to you that a chemical reaction or a chemical change has taken place. That's basically your apple reacting with the oxygen in the air, and it forms that brown stuff. So many times, sometimes you'll see, once again, you'll see the product being formed. Okay, you will see the product being formed. Now, what if you're cooking and you're cooking something and then you actually burn it and it turns black, right? When you burn something, that black stuff is basically carbon. That is an indicator to you that a chemical change or a chemical reaction has taken place. You actually see the new product being formed. Now, the last concept I want to talk about is the law of conservation of mass. So according to the law of conservation of mass is neither created nor destroyed. So in other words, the amount of mass that you start out with is the same amount of mass that you end up with. So now I'm going to go over some examples. Here is an example of the law of conservation of mass. So let's say we have carbon plus oxygen, and this is going to make carbon dioxide. That says carbon. Okay, so what do we call the items that are on the left-hand side of the arrow? So if you remember, in a chemical reaction, the items on the left-hand side of the arrow, these are called reactants. What do we call the substances that are on the right-hand side of the arrow? These are called your products. So once again, according to the law of conservation of mass is neither created nor destroyed. So the amount that you start out with is the same amount that you end up with. So let's say we have 5 grams of carbon and we have 5 grams of oxygen. We want to find out how many grams of carbon dioxide can be produced. Okay? So, once again, the amount you start out with is the same amount that you end up with. Therefore, the correct answer is 10 grams, okay? you can actually produce 10 grams of carbon dioxide according to the law of conservation. So remember over here, this is the reactant side, so 5 plus 5 is 10. The amount you start out with is the same amount that you're going to end up with. The mass is conserved.